Hello, everyone. Welcome to week 9 of this course. Before we go into the subject matter of the course, I just would like to relay some feedback from our graders regarding your write-ups. What they tell me is that some of you have been missing out on some free points on your write-ups by not including some of the some parts of the write-up. Okay, so the first thing is a header, and this header should include, say, the experiment title, the number, experiment number and title, author, section number, and the date that you're submitting this. Okay, so this header is sort of not just isolated to this course. You're going to have to include author and date and title of a document anytime you write up a document. So make sure you're including this, and it's worth 5 points for all submissions, for any submission. Okay. Second thing is objectives and conclusions. All tasks within a write-up must be framed within their own objective and conclusion. So each task must have one objective and one conclusion. And they're worth 5 points each for each task. So that's a lot of points. The third thing is whenever you're presenting data that you measured on a particular circuit, then you must always include the circuit schematic for the reference of the reader. Otherwise, the reader is completely lost in what you're presenting and what your data means. Okay, so this is good practice, and it's also worth 5 points for any schematic that you need to include. The fourth thing is labels and figures on tables. So anytime you include a figure or a table or a plot, then you must give it a figure number. Say, for example, figure number 3, plot showing whatever, right? Ohm's law or verifying Ohm's law or whatever, right? So a descriptive caption plus a numerical reference to the figure, right? So this is important that you start it is important that you start building these habits of including these things in your documents, because it's just good practice, okay? And so if you look at this, right, if you have three tasks that you need schematics for, then you have a total of 45 points right here, plus this 5 points, you've got a total of 50 points for free, right? For just writing the objectives and conclusions and including the schematics and headers. Okay, so this is not meant to penalize you, but rather to offer you free points so that you get a better grade, okay, on your write-ups. So make sure that you're including these elements of the write-up and get the points that you deserve. Now, the last thing is there are a few students who are still submitting handwritten documents that's as write-ups, and the graders have been kind enough to be grading these and giving you points for those. But a write-up should really be a typed electronic document. So nothing handwritten. So electronic document doesn't mean you can write with your iPen on your iPad and submit that. It has to be an electronic document that has been typed up. Okay, so if so far the graders have been nice enough to grade these, but going forward, I'm going to instruct them to not grade anything that's not typed up for the write-up. Okay. For circuit schematics, I guess I would recommend definitely using LTSpice or some other schematic generating software to draw the schematics. Don't copy it from your lab manual. That will not earn you any points. But if you find it difficult, it's also okay to just include a hand-drawn schematic, right? But it's fairly easy to do it on LTSpice, and I wouldn't see any reason why you wouldn't want to do that. Okay, so yeah, so that's the message I wanted to convey from our graders, and also from my side. Okay, so with that, let's move on to the subject matter of this lab. Okay, so the topic of this lab is step response and timing circuits. And before we start talking about step response and timing circuits, let's just recall the IV relationships of the capacitor and inductor. Okay, so the current voltage relationship of a capacitor and inductor is given here. And recall that for a capacitor, the current through it is equal to the capacitance times the rate of change of voltage across it. And the voltage across the inductor is the inductance is equal to the inductance times the rate of change of current flowing through it. Okay, so these are the fundamental IV relationships of inductors and capacitors, and that will give rise to what we call the step response and what we can use in timing circuits. Okay. Okay, so the first question for today is, what is a step response? And the answer is, well, let's first discuss what a step function means. A step function is any function that that changes value abruptly at certain point in time, right? So for example, here, the voltage Vs is V0 for before time t equals 0, and at time t equals 0, it abruptly steps to voltage Vf, right? So this is what we call a step response. Sorry, this is what we call a step function. So what a step response is um, the response of any voltage in a circuit due to the step function of the source. Okay, so here, if I look at the capacitor voltage, if I'm monitoring the capacitor voltage, and the source voltage Vs has this step characteristic, how does the capacitor voltage change due to this stepping function? Is what we call the voltage step response of the capacitor of this circuit. Okay, so I can also be monitoring the current through the capacitor, and as soon as I step the voltage Vs from V0 to Vf, then this current will also have some dynamics. And this dynamic behavior of that current is what we call the current response, current step response of the circuit. Okay, so that's just it. It's the response to a step voltage in the source. Now, the next question is, how do we solve for the step response of a capacitor or inductor in a circuit? For the circuit that I've shown you, this is just a quick example of how you can do it. We'll start with a KVL, and basically the source voltage must equal the sum of the resistor voltage and the capacitor voltage by simple KVL. And for time greater than 0, that source voltage is equal to Vf, and then you can replace the variables relevant to the circuit and do some algebra. Okay, so if you want to go through this algebra, you can pause and look at it, but I'm going to skip to this step here where you end up with this differential equation. Now the solution to this differential equation is the step response of the capacitor voltage. Okay, but here I would like you to make one key observation, and that is the units on each term. Okay. So the first term has units of voltage per unit time, right? And the second term has this form Vc, which has units of voltage, and divided by Rc. If we are adding these two terms together, it better be the case that the second term also has units of voltage per unit time. And that just tells us that this product R times C has units of time. And we call this time, we call this the time constant. Okay, time constant, usually denoted by a Greek letter tau. And it gives us the characteristic time scale of this circuit. You can definitely change it by changing the resistor and capacitor, but it gives us a characteristic time scale of the step response. Okay. All right, so I'm not going to go into how the solution for this differential equation is this. I'm hoping that you've covered this in your math courses. But basically, the solution to this differential equation has this form. And right now we have one unknown constant to solve for, and you can do that by using the initial condition for the voltage. Okay, so if you assume that at before time t equals 0, the capacitor voltage was some voltage V naught, then you can find that the overall voltage solution to this differential equation is going to be of this form. Okay, and this is also the full step response, a complete step response of the capacitor voltage. Now you can sort of do some algebra on this again and manipulate this to get it in this form. And what this is basically saying is that, so this is Vc of t. What this is basically saying is that at any instance in time, the total difference from the initial voltage is equal to the, let me rephrase that. So the deviation from the initial voltage at any instance in time is going to be some fraction of the total voltage difference from end start to finish, and some fraction of it. Okay, so for example, this delta V is actually, this delta V is actually the final voltage Vf minus V0. So if you go back to this picture, it's this step voltage, right? So the size of the step. And so basically what it's saying is that at any instance in time, if you multiply the size of the step by this factor, then you get how much voltage has changed from the initial point. Okay, and if we said that the tau is a characteristic time scale, the time constant. Let's look at what happens when after tau seconds of the step response, right? So if you replace t equals tau in this expression, what you'll see is that the total change that has occurred in the capacitor voltage is 63.2% of the total change that will occur for the capacitor. Okay, and so this exact relationship between the capacitor voltage given the time tau is what allows us to measure time by measuring voltages. Okay, so if we measure the voltage across the capacitor and you see that it has changed by 63.2% of the total step, then we know that exactly RC time has been elapsed. Okay, and so that's what allows us to make use in timing circuits. Right, exactly as shown in this picture. So the blue line shows the step voltage, whereas the red line shows the step response of the capacitor. And so the delta V is the total change in the voltage across the capacitor over time. But as it is charging, after time tau, the capacitor will have charged 63.2% to its final state. Okay, and so if you want to measure tau, then all we have to do is measure this total height in voltage, and then find where that height is 63.2% of the total height, and the time between when it started charging and this point will be exactly tau. Okay, so in task 1 and task 2, that's what you're going to do, is measure tau. Okay, so I've told you all about tau now, but the time constant tau, but why is it useful? So basically, as I said before, it gives us a characteristic timescale of the circuit. It tells us like how fast things are changing in the circuit. But why is it important in circuit applications? Is basically it allows us to time events, right? So like I said, by measuring the voltage, you can measure time. And we know very well how to measure voltages using oscilloscopes and stuff, right? So it allows us to time events quite accurately. And the second is by using this idea of the characteristic timescale, we can define different kinds of frequency filters, and these we will look at in lab 10, but just keep that in the back of your mind. Now I showed you an example for the capacitor, but you can do the same exercise for an inductor. The difference you'll notice is that the time constant in this case will be L over R, okay? So the differential equation will be of a slightly different form for the voltage. But if you look at the voltage response of the capacitor and the current response of the inductor, they will have a lot more similarities. Okay, so in this lab, we'll also get introduced to this practical circuit called the 555 timer. It is an integrated circuit that's very popular in making timing applications. But basically, what you have to understand about the 555 timer is that it has two comparators that control its output. Okay, so we've learned what a comparator is in lab 8. A comparator is basically a block that compares two voltages and spits out either high or low voltages. Okay, so in a 555 timer, we have two of these comparators. And the output of these comparators goes into this block called the SR latch. I won't bother you with the details of how the SR latch works, but basically these two inputs will control the output of the 555 timer. Okay, so the SR latch also has a second output, which is always going to be the opposite of the main output. Okay, but the second output of the SR latch in a 555 timer is controlling a switch. So if this voltage is high, the switch is closed. And if this voltage is low, the switch is open. Okay. So if you think about it, if the output is high, then the switch is open. And if the output is low, then the switch is closed. Okay. If you take that one step further, if the output is high, then the discharge is disconnected from ground. If the output is low, discharge is connected to ground, right? So keep that in mind. I know it can be a little bit confusing, but we'll come back to that in a bit. But let's look at the front end of the 555 timer again. So these two comparators, one of them is comparing a voltage to 2/3 VDD, and VDD again here is short for the supply voltage. So for example, if VDD is 10 volts, then 2/3 VDD would be 6.66 volts. Right? So this comparator is comparing a voltage, which you call the threshold voltage, to 2/3 VDD, and the second comparator is comparing what we call the trigger pin to 1/3 of the VDD. Okay, and the action is such that if this threshold voltage ever goes above the 2/3 VDD mark, let me start with the trigger. So if the trigger voltage ever goes below the 1/3 VDD mark, then it will set the output to high. Okay, so if trigger is less than 1/3 VDD, it will set the output high. And if the threshold is above 2/3 VDD, then it will reset the output to low. So that's all you have to understand about the 555 timer. And then also the fact that when the output is high, what happens to the discharge pin. but that's it. Okay, and now we're going to build different timing applications by connecting the threshold and trigger to different parts of the circuit, but we'll come back to that in a bit. Okay. Okay, so let's talk about the pre-lab. So the first task in the pre-lab is drawing a complete schematic of so-and-so figure by replacing the 5 to 5 timer. Okay. So in figure 9.21, you're shown a circuit block of the 5 to 5 timer with some peripheral circuits. But what you are asked to do is replace this circuit schematic unit with the actual circuit that's inside of it, which is shown in figure 9.13. So it should just be an exercise in copying two different schematics and combining them together, right? But this can be hand drawn. It's a very big circuit, and I think it might be easier if you hand draw it. But you can definitely also use AltiSpice to insert different blocks into your schematic and do it that way. Okay. Second question is asking you to calculate come up with an expression. Let's see. Yeah, no. So it's asking you to calculate the time it takes for VC to charge to the threshold voltage. So the threshold voltage, meaning whatever is the threshold voltage being compared to, so that's 2/3 of VDD. Okay. And you want that time to be in terms of R1 and C1, obviously, because it's going to be in terms of the time constant tau. Okay, and this question is referring to the circuit in figure 9.21 if it's not clear. So it's still talking about the same circuit. Now in task 3, you're going to design an astable 5 to 5 circuit to have an oscillation frequency of 1 Hertz and a duty cycle of 60%. So I know I haven't talked about these things in this briefing, but look at example 9.4.1 on your lab manual for the analysis for the circuit in figure 9.18, and also what this astable circuit means and what it means to have a duty cycle of 60%. Okay, so this third question for the pre-lab is a circuit that you will not be building in the actual lab, but it used to be a part of the lab. So we just want you to still be able to understand the oscillator circuit and to design for it at least, which is not having you do it in the actual lab because it makes the lab too long. Okay, but this is an important, very, very important circuit to learn and understand. So do go through example 9.4.1 in as much detail as you can and ask questions. Okay, so task 1 and task 2, what you're doing is you are estimating the capacitance and or inductance using time constant measurements. Okay, so in lab 7, I believe you did an experiment to estimate the capacitance and inductance based on the AC response, AC behavior of a capacitor resistor circuit, right? So you're doing a similar exercise, but now instead of measuring the AC response, you're measuring the step response of the circuit and measuring the time constants to extract out the capacitor value, right? So what you're basically doing is you're applying a so basically what you're doing is you're making this measurement of the capacitor voltage. It's charging from some voltage to other final voltage, and you're making this measurement. You're going to make this measurement. You're going to find the 63.2%, and then you're going to find the time elapsed. Okay, and this is going to be tau. And tau, you know, is equal to R times C. You know R, so you're going to find C. Right. So that's the short answer of what you're going to do in this lab, in this task. but let's go over some of the finer details and where you can, where it's easy to slip up. Okay, the first clarification is this first part here that shows a function generator or a square wave generator with an RS. This is part of the function generator. So this RS is not something that you will need to include externally on your circuit. Okay, this is part of the 82. And in fact, for 82, RS is equal to 0. So you also do not have to account for it in any of the calculations. Second thing to talk about is this RESR. So this RESR is also not something that you need to include separately in your circuit. It is part of the capacitor. Okay, so an ideal capacitor would just be this, but real world capacitors have some dissipative, show some dissipative behavior, and that is modeled by what we call the equivalent series resistance of the capacitor. Okay, so this is part of the capacitor, and anytime you include a capacitor, it's going to be in there. So typically, we would have you measure the RESR using your DMM, but for a capacitor, using an LCR meter, but but since you do not have an LCR meter, you won't be able to measure RESR. Instead, we've given you the RESR value to use. For an inductor, however, you can measure the ESR value by simply measuring the resistance of the inductor, okay, using a DMM. You cannot do the same thing for a capacitor's ESR value. Okay. All right. So the next thing to keep in mind here is in step 4, you are asked to generate a square wave that goes from 0 to 2 volts. So basically that means your square wave should start at 0 volts and go up to 2 volts. Okay. So now think about what the amplitude and the offsets need to be to get this signal. The second thing here is you're asked to find a reasonable frequency. And the question is, what does reasonable frequency mean, right? So you have to use this idea of time constants again. You know what capacitor you're using, and you know the series resistance attached to it, right? So you have an idea of what the expected time constant is. Now you're going to have to pick a frequency so that in each half cycle, the capacitor has enough time to charge. Okay, so if your frequency is too fast, then the capacitor may not get enough time to charge all the way up, right? So you need to choose your frequency so that the capacitor has enough time to charge in each half cycle. Okay. Now, in step 5, the instructions ask you to measure Vs and Vc, but what you really need is Vc and Vsense. Okay. Again, Vsense is gives you a measure of the capacitor current. So that's what you need Vsense for. But since 82 has a differential probe, instead of measuring Vs and Vc and taking the difference to calculate Vsense, you can directly measure Vc and Vsense. Okay. All right. Yeah, so step 7, you're going to capture the oscilloscope screenshot and show measurements for tau, as you did in step 6. And in step 9, you're asked to compute the percent error for the calculated capacitance value against a measured capacitance. So cross off this measured and replace it with labeled capacitance. So basically the labeled value is this 2.2 microfarads. You cannot measure the capacitance since you do not have a LCR meter, but you can compare it to the labeled capacitance value. Okay. Now, the last task here, last step of this task is to plot plot the measured voltage against the ideal step response. Now, the ideal step response means the theoretical step response that you get by doing the algebra and calculating the solution to the differential equation. And you're going to export the oscilloscope data and plot that alongside the theoretical response. Okay. You're also asked to plot the ideal current response. This is again the theoretical step response of the current through the capacitor. And you can also get the current values for the capacitor current by exporting the data from the vsense measurement. Okay, and so you're going to use either Python or MATLAB or any other plotting tool that you know to plot these data, and as well as the analytical plots. Okay. All right, so task 2 is basically the same exercise, but with an inductor instead. And you will see similar voltage waveforms, but the current and voltage waveforms will be swapped. And for an inductor, RESR is not given, but you can definitely measure it with the DMM set to resistance mode. Okay, let's talk about task 3. So in task 3, we're going to use this capacitor charging profile or the characteristic time scale of the capacitor charging to design a timed circuit called the light doorbell. And basically, the idea is to design sort of a doorbell-like light, which stays lit for 5 seconds after pushing a button. Okay, so it's meant to be for the hearing impaired. Instead of a bell, you have a big flashing light that goes on every time someone presses the button to the entrance. Okay, so that's the idea behind this circuit. And what we're using to make the circuit is a simple capacitor charging circuit coupled with the 555 timer. Okay, so there's a circuit schematic shown in your lab manual that gives you the full circuit that you need to construct. But in order to explain, I'm just gonna take parts of this circuit and ignore some of the parts that don't contribute functionally, but are equally important. Okay, so first of all, I want you to concentrate on this part, R1 and C1, right? So this is the functional part of functional timing circuit. Basically, you have a capacitor being charged through a resistor, and it's a simple RC circuit, right? So if left to its, so if this circuit is left on its own, the capacitor voltage will increase from 0 volts all the way up to 5 volts, and it will stay there. Okay. Okay. Next, let's look at this output pin. This output pin is connected to what we call a light emitting diode or an LED. And basically it lights up whenever the output is high. Okay. Okay. Now let's look at this trigger voltage. This trigger voltage is connected to 5 volts via the R2. And whenever this switch is open, this is an open circuit, so the trigger is always at 5 volts, unless you push the button, and in that case, the trigger gets connected to ground. Okay. Now let's put all of this circuit together. First of all, let's start by connecting. Let's start by connecting this discharge to the capacitor. Now, what this does is, well, it connects the capacitor voltage to the discharge, And if the switch is closed, then the capacitor gets discharged to ground. If the switch is open, then the capacitor can continue charging from this 5 volts. Okay, so take the time to pause and think about that for a while. All right, now we'll plug in the most important connection, this capacitor to the threshold voltage. Okay, so what this is doing is we're attaching this capacitor voltage to this comparator, which compares it to 2/3 of VDD. Okay, if this capacitor voltage is lower than threshold, then nothing happens. If this capacitor voltage is higher than the 2/3 VDD, then it will reset this output to go low. Okay, and this LED will turn off. Okay, so that's the function. Now let's trace what happens when we push the button. Okay, so let's assume that at the beginning, the output is at low and the LED is off, the switch is open, and the capacitor therefore is discharged to ground since this switch is closed. Right? So the output is low means this is high, means the switch is closed, means the capacitor is connected directly to ground, which means the capacitor voltage is 0. Right? So that's our starting point. Now, as soon as I turn on this switch, the trigger voltage is pulled to ground, right? That is, the trigger voltage goes below 1/3 VDD, and so it sets the output to high. That turns on the LED, and it sets this node to low, which opens up the switch. So the capacitor is no longer connected to ground, and the capacitor can start charging. Okay, so let's see what happened here. So if we make a graph here, so the capacitor voltage was at 0. As soon as I press the switch, the capacitor starts to charge. And also, as soon as I press the switch, the output goes high. Okay. Now the capacitor is going to continue to charge until it reaches 2/3 VDD. So if this is 2/3 VDD, at that point, this comparator gets activated, right? This comparator gets activated as the threshold voltage increases above 2/3 VDD, and that will basically turn off the output, and it will turn on the switch, and that will discharge the capacitor, right? So what happened here? As soon as the capacitor voltage reached 2/3 VDD, the capacitor got discharged, and the output got turned off. Okay. So now our task is to make this time interval between when the capacitor started charging and when it gets discharged to be equal to 5 seconds. Okay, we have the capacitor equation. We have the characteristic time scale of the capacitor given by RC, and we can use math and algebra to pick resistor and capacitor values so that this time to go from 0 volts to 2/3 of VDD is exactly 5 seconds. Okay, so this is actually the exercise that you did in pre-lab. All right, so that's this circuit. I know this circuit can be a little bit confusing and hard to keep track of what's going on, but think about it for a few minutes and then try and get an understanding of what this is. Okay. So for this task, I have a few comments here in choosing R1. For choosing R1, I would recommend that you stay below 100 kilo ohms. If you pick anything above 100 kilo ohms or closer to 1 mega ohm, then making measurements on the circuit will change your circuit, right? So if you remember that an oscilloscope or voltmeters, they have also some resistance associated with it, which is closer to 1 mega ohm. So if you have a large resistor in your circuit and you're making measurements close to that resistor, then the act of measurement alone can change the circuit and make your circuit behave differently than what you expect it to. Okay. In step 3 of this task, it talks about using a 10x mode and whatnot to avoid the same issue I was talking about earlier. But the 82 does not have this 10x mode, so you can just ignore that part and just stick to using an R1 that is less than 100 kilo ohms. The third thing to point out is that the pin out of the 555 timer is considerably different from the schematic shown. Okay, so don't assume that the schematic follows the pin layout of the package. Okay, so Google the pin out of the package, pin layout of the package, and use that in constructing the circuit. Okay, and finally, for those who are doing the LT-Spice version, email me to receive a copy of the LT-Spice version of the tasks, but the tasks should be exactly the same as the 82 version, except that you will do it on LT-Spice. And yeah, for the inductor RESR, you can simply use the same ESR value as for the capacitor if you cannot measure it. Okay. All right, so that is all for this week's lab. If you have any questions, do feel free to reach out to me or to any of the TAs with questions. And keep in mind the comments from the graders regarding things that you're missing in your write-ups. Do make sure to include them. All right. Thank you for listening to me, and good luck with this lab.